Welcome back, Physics 30. This is CO2.3, collisions and impulse. So last time we looked at momentum and we looked at the conservation momentum. Now we're going to relate it to something called impulse. So define impulse and write the equation that connects impulse and momentum and solve problems involving impulse and momentum. So collisions are common occurrence in everyday life. For example, a tennis racket or a baseball bat striking a ball, billiard balls colliding, a hammer hitting a nail, etc. When a collision occurs, the interaction between the objects usually is far stronger than any external forces. Therefore, we can ignore the effects of any other forces, even gravity, during that brief time of collision. So a hockey stick hitting a puck, very large amount of force involved, and we can just simply look at it for that short time period. During a collision of two ordinary objects, both objects are deformed slightly. Even in this tennis racket, you can see that. Or if you look at a hockey stick hitting a puck, a slap shot, that hockey stick bends considerably because of the large forces involved. When the collision occurs, the force each exerts on the other usually jumps from 0 at the moment of contact to a very large number and then goes back to 0. So if you look at this graph at the bottom, it kind of illustrates that. So it's not just one force. It starts off at 0, some maximum force, then decreases to 0. So it actually looks like that. But over here, we're going to look at, well, we can simply take the average, or looking at the kind of maximum force that's involved there. So a graph of the magnitude of the force, so we saw that below. The time interval is usually a very small time interval and very distinct, typically a few milliseconds for a macroscopic collision. For Newton's third law, as seen earlier, the net force on an object is equal to the rate of change in momentum. So we looked at that before. And remember, delta P is m delta V. And of course, change in V over change in T is really acceleration. So really this is the F equals ma equation, but kind of illustrated in terms of change in momentum. So we have written F instead of sum of F for the net force, which we assume is entirely due to the brief but large average force that acts during the collision. So we're going to look at the large average force. This equation applies to each of the two objects in a collision, and if we multiply both sides by t, we get this. So change in momentum equals F multiplied by delta t. And this part of the equation, so all I did here is just simply multiply each side by t. So I'm looking for change in momentum. This side has a specific name. And that specific name is referred to as impulse. So the quantity in the left, the product of force times the time over which the force acts, is called impulse. Because the change in momentum, to make a change in momentum in something, you have to exert a force and you have to exert it over a large time period. So if you want to make a large change in momentum, like going from 0 velocity to some maximum at a short time, you want to maximize. So we can kind of think of this is the contact scenario. So if you can maximize the time of contact, so for example, that tennis racket on the previous page, if you can maximize the time in which that racket is hitting the ball, or maximize the time in which a hockey stick is touching a puck during a slap shot due to being bent, and make as maximum force as possible, because sometimes you can only make such a certain amount of force, but if you can maximize the time of contact, F times T results in a larger change in momentum. So those two variables can be manipulated, and those are manipulated quite frequently in sports. For example, hockey sticks in the 80s, they were made of wood. Now they're made out of other materials that can bend without breaking. So we see that the total change in momentum is equal to the impulse. The concept of impulse is useful mainly when dealing with forces that act during a short time interval. The force is generally not constant, and often it's a variation in the time, like that seen in the earlier graph. We can often approximate by just looking at that large average force that we're looking at. All right, so there's one example here, then you'll be able to do the assignment. So for example, a karate blow. Estimate the impulse. So the impulse which is F delta T. And it's a weird unit, newtons times seconds. And of course that's equal to mass times V, kilogram meters per second. And the average force delivered by a karate blow that breaks a board. Assume the hand moves at roughly 10 meters per second when it hits the board, and the contact time is 2 times 10 to the minus 3 seconds. There's one thing I forgot to put in here, and it's the mass of the hand. Mass of arm/hand, we'll say, is 1 kg. Okay, so that's the only thing we need. So if we're looking for impulse, which is F delta T, of course we're told time, but we're not told force. So we're going to have to manipulate this a little bit. Of course, impulse is equal to change in momentum. And we do know material involving change in momentum. So remember, before P is equal to mv, or if I'm looking for change in P, it's mass times change in V. So the change in velocity, which is mv2 minus mv1. So by the time I hit the board, my hand is moving 10 meters per second. So initially, of course, your hand is moving 0. So the mass is 1, 10, 1, 0. So 10 kilogram meters per second. Whoops, I kind of messed that up. So change kilograms times meters per second, so kilogram meters per second, which is equal to, if I change it to this unit here, Newton seconds. Newton seconds. Kind of a weird unit, but that is the unit for impulse. Okay, and then lastly, what is the average force? Well, I have F delta T is equal to change in momentum, or if I use the equation from before in the other video, I can just rewrite it like that. So my 10 divided by the time of contact, 2 times 10 to the 3 minus 3, that works out to be 5,000. That will be units of newtons. Right, so there you have it. So that's CO2.3. So you should be able to do the assignment there, dealing with the introduction of impulse and its equivalent to change in momentum. See you again.